So, the next topic that we want to talk about are balance laws. So, if I want to model a fluid flow, it is based on certain principles, certain laws, and we know a few of them already. For example, we could say there could be mass balance, or for example, we could talk about force balance, or for the matter, we could talk about energy balance, and so on. So, in fluid mechanics, the mass balance leads us to what is called the continuity equation. The force balance would actually relate the force applied on a fluid, body force as well as surface forces, and that would be the rate of change of momentum. So, these lead to what are known as the momentum equation. And they are also referred to as the Navier-Stokes equations, because these were first derived by these two scientists, Navier and Stokes. So, these equations are very special, named after them. And of course, we could have the energy equation. Now, the energy equation, as you know, would involve something like internal energy, the kinetic energy and so on of a system. So, it would involve temperature, for example. In this course, we would be actually talking only about the mechanical energy of a system, which would be related to the potential energy, kinetic energy and so on. So, it is a very special case of what one would see in general. Now, there is so we would like to write these equations for the fluid, but as you are aware that these laws, they are usually for a controlled mass system. What that means is, if I look at force balance, for example, then there is a particular amount of mass that I choose, and I try to figure out what are the forces acting on it, and that would decide then what is the momentum change to that mass. Same thing with energy, same thing with mass balance. But in fluids, a control volume is more suitable, convenient or suitable. In the sense that I cannot follow a fluid particle from the time it starts moving up to the time that I am interested in, that it could move quite a bit, and to track all that region would not be such a good idea. So, I would like to instead keep a small window or maybe a large window, and then look at fluid elements that come into it and probably exit that after some time, and look at the balance of what happens inside this window. So, that is a control volume approach. So, an example of a control volume, for example, would be a jet engine. So, here is a cross section of a jet engine, where you see this is the cowl of the engine, and you could have some components inside. For example, you could have maybe a compressor here which is driving a turbine, and they are connected by a shaft, so they spin together. You could have a combustion chamber, so this is where the combustion takes place. and therefore it gives out energy that would give rise to a high speed jet. So, I could have fluid coming in, maybe there is some fluid that does not really enter the engine, it goes from the outside, and then I have some fluid that goes from here. So, I am showing you a jet, I am not showing you all the streamlines. We now know what streamlines are. Okay, so they could go through some very complicated motions inside, so I am not showing that. But roughly speaking, this is the flow that I could have, right? And now I want to do a control volume analysis. So what I could do is, I could say, well, instead of following a fluid element that is a control mass and it goes through the entire engine and exits out, which would be very complicated, I actually do my analysis on a region like this. So this here is the control surface that encloses control volume. So we are going to use some abbreviations. So control surface, I would usually refer to it as CS, and a control volume, I would refer to it as CV. Okay. So the idea is, I want to set up a balance law, for example, a force balance, that there is some force acting on this control volume. It could be because of surface forces like friction, it could be because of body force, maybe gravity or some other forces. And then I would relate it to the momentum of the fluid that comes in versus the momentum that goes out and the rate of change of that. And same thing for energy and for the mass balance. So I would like to develop a framework that kind of goes from a control mass to a control volume. So my balance laws are more suited for a control mass scenario, but I want to apply them to control volume. So I want to develop this framework. So we need some kind of a framework. And this is made possible by what is called as the Reynolds transport theorem. So this theorem would take a control volume and try to apply these balance laws to this particular control volume and not just to a control mass. Okay, so let's try to see how it works. So to illustrate the idea of the Reynolds transport theorem, what I would do is, let me consider a body this is a hypothetical body which has, so this is a control volume that I am considering. And there is an inlet port and there is an exit port. So I am taking a very special case where fluid comes in through the inlet port and it leaves through the exit port. There could be many inlet ports, there could be many exit ports, but this is a very special case just to show you how this works. I am further going to assume that let n be the unit normal. So n is the outward pointing unit normal. So whenever there is an inlet port or an exit port, I first figure out a normal which is pointing outward. As you know, the surface will have two normals, one pointing inside and the other one pointing outside. So I pick the one which is pointing outside. Then at the inlet port, I could say, well, this is my inlet velocity Vi, and this could be my exit velocity Ve. So this is inlet velocity, and this is exit velocity. I am also going to assume that I is the area. So if this is a cylinder, for example, a cylindrical cross section, or it could be any other shape. So this is the area of inlet, and likewise I could have AE as area at exit. In fact, I could use them as vectors. If I say that it is area times the unit normal, then they become vectors. I want to understand what happens to a certain property n. So let us say there is a property n of t whose balance I wish to study. I will say let eta x of t be the specific property, which actually implies per unit mass. Okay. So if I want to if I am interested in nt and I want to relate it to eta xt, then they are related by this. So this is, I would integrate over the control volume. So let me say this is V, where V is the volume of the CV, this entire control volume. So I integrate over it. So this is a property per unit mass, and I would like to get the mass of an infinitesimal quantity. So then I would have to do it like rho dV. So the idea is, if I am interested in what happens to, let's say, energy inside this control volume. So first I figure out what is the specific energy at different points in this control volume, and then I integrate it over the entire control volume, and that gives me n. So I could possibly make a small table and show you what. So suppose this is the quantity that I am interested in, this is n, and this is. So suppose I am interested in mass, then my n is the total mass of the fluid inside the control volume, and as you can see, eta would be simply 1, because if I put eta equal to 1, then rho dV would actually, if I integrate it, give me the total mass inside my control volume. Similarly, if I am interested in momentum, then actually I am interested in the integral of this momentum, and here I would simply say V. Okay. And if I am interested in the total energy, then you can see that the specific energy would be simply E, where E is the specific energy. And this E, sorry, this is not a vector, it is a scalar. So E, for example, could be half of V square if E is the kinetic energy only. Of course, I could take other definitions if I am interested in other forms of energy. So there we go. So I am now interested in what happens to the property n in this control volume, and eta is my specific property which could be which are defined like this. So I am going to ask myself a question that suppose n, capital N is the property inside the control volume. How does it evolve with time? Okay. So n of t is the property in control volume. So accumulation of n t in the control volume. What are the processes by which n could actually change in the control volume? So this I would say would be simply del n by del t. Okay, this is the rate of change of n inside the control volume because I am fixing the window. Right? This actually could happen because of three processes. One is I could get a generation of n. What this means is that I could have actually the material growth and this corresponds to dn by dt. So this is one way. So if I am interested in, let's say, how does the mass inside the control volume increase, so one way is maybe mass is getting generated inside the control volume. Okay. The other is I could get some influx into the control volume. So there is an inlet port and maybe some mass is coming in through this inlet port, and that contributes to the growth of mass inside the control volume. Or I could be having efflux. So let me denote this by I dot, this is influx, and efflux by E dot. So essentially the equation is that del n by del t is dn by dt plus I dot minus E dot. Let me show you graphically what these terms mean. So here is in this red box or in this red surface, the control volume, the fluid present at time t. Okay, so this is the fluid at time t. If I want to track where this fluid is after time delta t, well, maybe this fluid has gone somewhere here. I am just drawing it roughly, and this fluid has gone somewhere here. So maybe I could get a picture like this. Again, I should draw it in broken lines, but just to save time. So you can see that the fluid is being pushed out of this box. And I could also ask myself, where was this fluid delta t earlier? And then I would say maybe it was here. So I have just roughly drawn it just to show you. Okay. So, what has happened in time delta t, this green fluid is pushed inside the control volume, and after time delta t, this red fluid is pushed out as blue fluid outside the control volume. If I want to apply a balance law, I have to follow the same fluid elements at all times. Okay. So, I would have to look at how the green envelope of fluid actually becomes red and then finally becomes blue. It is the same set of fluid particles, but that is too complicated. So, therefore, I am going to restrict myself to what is happening along this red dotted control volume. So, that is what this term is, that at time t, if I look at the total property inside my control volume, how that changes is del n by del t. Okay. This could be something which is growing inside. Maybe there is some kind of a chemical reaction which is producing some material, and that would contribute to this term. And likewise, the influx is the quantity that is actually the green one. So, I will circle it with the green one. And the efflux is actually the blue one. So, maybe I will circle it with the blue one. So, I can now calculate what is I and what is E. So, the proposal is that I dot is actually this quantity, the property within this quantity that has come in. So, I could say that this was travelling at a speed V_I, and this is the time. So, V_I delta t, and I would dot this with the area A_I. Then this is the volume flow rate, and if I multiply with rho, that becomes the mass flow rate, and this multiplied with eta of x t and then divide by delta t, this becomes the rate. Okay. So, I hope you have understood what I have done. So, this is the extent in which the fluid particles have travelled. So, that is the distance. I am taking the dot product with the area. So, that is the flux that is crossing the inlet port. From this, I am able to get what is the mass flow rate, and I multiplied with the specific property, and then because I am interested in a rate, so I again divide by delta t. And this quantity therefore turns out to be rho Vi dot Ai eta. Notice that this should have a negative sign because my V and A are in the opposite direction. My velocity is pointing towards the unit normal, and therefore, I must take a negative sign. Okay. Similarly, I could calculate what is my E dot, and that is easy to see. So, I will simply write that for you. So, that would be rho VE, this is dotted with the exit port and the property eta. So, if I combine these equations, then I am able to write del n by del t is dn by dt. This is the influx, which is minus rho V inlet dot A inlet, which is also a vector. So, I am sorry, I forgot to put a vector sign because this includes a unit normal. And then I have the efflux, which is minus rho V efflux. All right. So, this is the equation for the Reynolds transport theorem for this control volume. So, what it says is that the rate of accumulation of the property n inside the control volume is related to what gets generated there, and then what comes in and minus what goes out. And of course, I explained you why we get a negative sign in the influx term, because Vi and the area, the unit normal, they are opposite in direction. This equation I have written only for one inlet port and one exit port. It could be very easily generalized for multiple inlet ports. So, you would have to add several terms if you had multiple inlet and. But I could actually do it for a more general setting as follows. I could say that del n by del t is actually dn by dt minus, I could carry out an integral over the entire control surface, and this is rho v dot dA. Okay. So, v is the velocity at the control surface, dA is if I take an infinitesimal element at the control surface. So, what this would imply is that if this is my volume, then I would have to take an infinitesimal area over here, look at the unit normal times the small area, and v is the velocity which is approaching the control surface. Okay. If I want to expand it, then what this would mean is del by del t of an integral over the control volume. I have rho eta dV. So, that is the first term. This would be d by dt of and then I have this term which is minus the integral over the control surface rho v dot dE. This equation here is the Reynolds transport theorem. What it does is, it tries to tell us about the conservation or the evolution of the property n in a control volume system. The way this term has to be interpreted is the following. I have a control volume. So, this gives me the property of the fluid, it could be mass or energy inside the control volume at that time instant. And I am looking at now the material derivative of that particular mass of fluid, that particular property of the fluid enclosed by the control mass as it moves in time. Okay? All right. So, we can now apply it to different quantities like mass, momentum, energy, and then get the various balance laws.